independent B prime. So what that's going to be is this. With the independence. Right, so you can always choose a basis that's independent over the parameter defining the vector space. And then what do we know? Well, A is in the C span of B prime. Right? So in particular, A can be defined over B prime by some constants. And that's the vectors, the differential field generated by the constants in B prime. Right. So this type is C internal.
Do you have an example of something that is not C internal? No is fine.
Sorry?
No is a fine answer.
I don't know if there should be lots of things.
Oh, of course.
Yeah.
Almost everything.
Yeah.
Yeah. I mean, the question was,
It's
is there
tricky.
something that's where it's easy to trace through the definition?
Oh, vector space. No. Not a vector space.
No, vector
Yeah. I don't,
Elliptic curve. How about that?
well, okay, so.
yeah. But probably most things should not be seen.
Oh, yeah, of course.
Yeah.
All right. And now we're going to strengthen this a little bit. So I'm going to erase this one so we still have this definition up. So the jet space.
When you write B prime C, you actually mean B prime comma C, is that correct?
Yeah.
Well, this is again the field generated, the
By
differential
B.
field generated.
Well, you have a
over C by-
multiplication.
By B.
I just want to make sure you're not.
Yeah.
not
Correct,
multiplication.
Yeah. So
Yeah.
I'm just going to like list tuples.
Oh, okay. I mean, I just want to
Juxtaposition
understand
and
what
model theory.
Yeah, it's the same as KB in the original.
Yeah.
So the jet spaces were originally introduced by Pillet and Ziegler, and they used it to prove this canonical basis property, which, so we end at 11:30?
Well,
45.
45.
well,
Okay.
the real issue is that it's completely up to you.
Yeah.
But at 12:30 you have to start talking in the model theory seminar, and you might want lunch before then.
You better eat.
So maybe I can talk more about the canonical basis property if we continue in the afternoon.
Oh, okay, good.
But C internality is something that shows up in this. So the canonical basis property says if you take the canonical base of something, then this gives you a C internal type. And they use this to show the dichotomy theorem for differentially closed fields in a simpler way.
Dichotomy between constants and modular?
Yeah. So they use C internal, and they took this from something that happened in compact complex manifolds,
Oh,
which was a theorem from like the canonical basis theorem.
oh.
Yeah. I don't know where this first showed up in model theory.
Oh, it changed. I mean, it's Sherlockian.
Yeah.
William.
No, I mean
or
the model
almost
theoretic
internal.
notion. This notion of almost internal.
Yes, and I think it first occurred in William and then Pillet worked with him.
No.
Oh, yeah,
in
yeah.
general, in model theory, it's from Shellow's
Pillet.
classification theory.
Pillet.
Shellow's classification theory, 78.
Oh, yes, Schiller, yeah.
Yeah. Right. So that C you can put other things here,
Independent of
and in compact complex manifolds you put projective space. But this canonical base property came from compact complex manifolds, and a theorem of Campana in 1980, I think, and also I think Fujiki in 82. But what they showed is actually more than what is the canonical basis theorem. They showed that something is called a Moishazan map. And so Moishazan is something that's sort of stronger than C internal. And the next thing we're going to find is something that captures more of what it is. It's not exactly the same thing, but it captures more of the flavor.
So this is halfway between C internal and Moishazan?
Between like C internal and algebraic over C.
Oh, between C internal and almost C internal?
Oh, so, no, between almost C internal and actually being algebraic.
Oh, without the B prime.
Yeah.
Got it, okay.
So this is called preserving internality. Let me see, I wrote down C, but I shouldn't use C because it's not going to be clear. Let me use D. So this is basically about base changes. So I can say in a second what this means. Yeah. What this means sort of non-model theoretically. But the idea is it's type A over B. You say it preserves C internality. If whenever you take some D, right, so the idea is you're looking at like A, then B, then D. So this type preserves C internality. If whenever this type is C internal, then this type is. Or sorry, then this type is. Right, so anytime you add to the base some sort of sub extension that's internal, then your new type over the new base is internal. So right, so if this one is C internal, then this whole type is C internal.
And
So
it's clear that almost C internality implies preserving C internality by some sort of
or vice
working calculus.
versa. So preserving C internality implies almost C internal. So if you take D to just BB, right, then this is C internal. So then what you get is A over B is C internal. Yeah, so C internal is implied by preserving which is implied by being actually in the algebraic closure of the constants.
Together with B?
Yeah.
So type A over B is C internal? It's almost C internal? If it
Yeah.
preserves,
If it preserves, then it's almost C internal.
Oh,
So it's
why does
a
the
strengthening
How does that
concept.
happen?
Why does the converse fail?
So it might be that B is sort of some non-independent parameters that you need to witness this algebraic closure.
So you
Right,
can't
so you couldn't have
somehow-
added them in.
So you can't do some sort of forking calculus to move the extras that you needed to go from D to
I
B
see.
away from depending on
Yeah.
A?
So you can think like maybe B is A, right?
Yeah.
Oh.
That's C internal,
Yeah.
right? Because you're
Well,
automatically.
but then it also
then
preserves
you-
internality. Because then the preserving
Oh, yeah.
internality is tautological.
Yeah, sorry. That's true. Yeah, but you might, right, the point is that this is sort of like this is like a two-step internality
Yeah.
analysis, right? And then a one-step is not always,
Oh, okay,
Right.
got it.
right? This is
yeah.
sort of like
Yeah.
it can't be like
Yeah.
a top step of analysis.
Yeah. Thank you.
Did you define C internal without the almost?
No, so there's always an almost, even if I don't write it.
Oh, almost an almost.
Yeah.
Always an almost.
Yeah, so there is something that has no almost.
Almost always.
If you take out the almost, then you put a
And
definable
it's
closure
right
here.
inside of C. Is that what it means?
No, it means, so this is a definable closure.
No, without the almost.
Yeah.
Differential-Algebraic.
If it's in the definable closure.
Yeah, of these things.
Actually.
That's called actually
Oh,
central.
that is C internal. Oh,
Yeah.
okay.
Like his example when you wrote almost internal, he meant almost in the actual.
Okay.
Yeah.
So what was the theorem that was proved of Mush's on maps?
In compact complex manifolds. So I have to admit, I don't know very much about compact complex manifolds. It's mostly my co-authors who knew it, and then I was sort of going from the model theory on. But so it was sort of like a completely geometric theorem. And it said that a certain map is a Moishezon map. And so if you translate into model theory, it's basically saying that something about like a canonical base, which is in differential fields a minimal field of definition, has this property. Plus it had a bit more in the compact complex manifolds. All right, so now I want to say what this means differential algebraically. Let's see, what am I? So if you have a rational map, which is dominant, and it's defined over K, which we assume is algebraically closed. Let me see, what do I want to call the varieties? So it's a map. X goes to Y, I think. I think this works out with the notation right now. So we say that this preserves C algebraicity if whenever you have some subvariety of Y, and it might be defined over some, let me see, I wrote down L here, but I've used L. Let's use F. So it's defined over some extension of your base field where X and Y are defined over, and your morphism, right? So you've extended your base, which has sort of right, made your variety smaller. Okay. And if V is C algebraic, the other thing is that V should still share generic points with Y. Right, so still there's some generic point of V that is also generic point of Y. Right, so we haven't completely looked at some non-dense part of Y. Then your inverse image in X is again algebraic. Right, so it's basically saying that the subvarieties of Y can be pulled back to C algebraic subvarieties of X.
What does C algebraic mean?
So that was this thing that was like C internality, right? Being basically birational into the constants. Right.
Define over C? No.
No. So remember this one that we had C internality, and then you said, oh, that should be.
C internal? Almost C internality?
Yeah, it's the sort of the differential one, right? Remember we had. Right, this was the one that you said, like, you finally understand internality.
But it didn't say C algebraic.
Yeah, so we called that C algebraic.
Oh.
Right, so this is the one where you had
Descends to constant.
have these maps like this.
Extension. So almost C internal. Can I put that instead?
Yeah.
Equals C algebraic.
What are the conditions on X and Y?
So they should be, so they're defined over K, and they should be irreducible.
Differential
I'm sorry.
varieties.
Differential varieties.
Algebraic?
Differential
Different.
varieties.
Irreducible.
Right, and then you pull back subvarieties of Y into algebraic subvarieties of X.
So you're saying that something is birational to Y has to pull back. Something that's C algebraic.
That's what it looks like, doesn't it?
Yeah, and it has to, right, it has to pass through a generic point.
Which is,
Remember that V is, right, so
just to
the
make
idea
sure,
is,
just to make sure for you, irreducible means absolutely irreducible?
yeah,
Okay.
yeah, right, these are supposed to correspond to types. Right, so then the idea is, basically these two things are the same.
Oh, I see, yeah.
Right, you have to do a little bit of move, right, because this is defined as a sort of a projection map, right, you have to figure out exactly what X should be over here. Right, but it's basically like the projection of, I think it was the projection of like AB
Yeah.
to A.
Wait, actually,
G.
I think saying that it's about types doesn't get absolute irreducibility. Suppose that
Oh,
my
yeah,
little
sorry.
k is the base field and my little a is the square root of a transcendental little b. That's irreducible over kb, but not irreducible over the algebraic closure. And then you would
Yeah.
have interesting proper pieces showing up as v's.
So I guess the type should be stable types. Probably.
Okay.
If the splitting.
Whereby stable you mean
Sorry, not
stationary.
sorry.
Stationary.
Yeah, sorry.
So yes, when
Yeah.
you say irreducible, you mean absolutely irreducible.
Yeah.
All right. So, all right, so this is something that showed up sort of in this form in the compact complex manifolds. And the idea that we had is basically try to find examples of where this could show up in differential algebra, right? Like, you know, there's this idea that things should transfer somehow. So if this is something that's important in compact complex manifolds, we should at least be able to find examples of this in differential algebra.
Almost C internal.
Of preserving C algebraic
Preserving
C.
C algebraic.
Or preserving C internality. Right, so C internal has examples because we have these C vector spaces. Right? Any C vector space is almost C internal. But this is a stronger thing. And so the question is, where are there examples of this? And then the natural place to look is jet spaces, because in compact complex manifolds, there are jet spaces, which Pillay and Ziegler sort of took over to make the jet spaces here. And they had this Morchazon property over there. So the idea was to show that they have this property over in differential algebra. So the theorem So I'm going to write the model theoretic statement first. So if you have a finite dimensional differential algebraic variety irreducible, then C internality is preserved by the generic types of the differential jet spaces to X at any point. Right. So this is something that gives examples of this preserving internality.
So what you're saying is that the type of the generic point in the jet space
Over
over
the point on
the
the
relevant point on the variety
Yeah.
preserves internality.
Yeah.
It's so strange because it's so much like it is a vector space.
Any
Oh, in.
Yeah, but it's sort of a special vector space.
various.
Right. So it's not true that every vector space preserves the internality.
Yeah.
Are your statements about C internality, are you restricting always to finite dimensional delta varieties for the definition, et cetera?
No, I don't think so. Right. Yeah.
You have to if you're the conclusion forces finite
It
dimensionality
forces it to be,
because it forces
Yeah.
it forces you to be algebraic over. I guess your little
C internal.
I guess your little a could be infinite dimensional.
Yeah. Right?
Okay, so yeah,
Yeah.
no, it doesn't.
It
My bad.
doesn't?
Yeah.
It's somehow what it forces is somehow relative finite dimensionality.
Yeah, so, because, yeah, when you extend fields in differential algebra, you get things that are not finite dimensional.
Yeah.
Yeah. And I should just say something here, right? So X is only a finite dimensional variety, and we define the jet spaces for these algebraic D varieties. So of course we can transform this into an algebraic D variety. There's also a definition of a jet space which is a lot more complicated. In the arbitrary case, I think this is Musa and Tom Scanlon did this. But you can just think of this as always turning it into an algebraic D variety, and then looking at the jet spaces, we defined it there. And probably it's helpful for me to write down a differential algebraic translation of this.
Oh, yeah.
Right, and this is basically that the jet bundle map preserves the algebraicity. Right, so basically what that's saying is that, so here, right, X is the jet bundle projecting onto the variety it's the jet bundle of. And if you restrict the variety to some algebraic part of it, then when you look at the jet bundle of the original one, but restricted only to points over this subvariety, then you get something that's the algebraic. Right, so if V is a subvariety of Y, and it's C algebraic, and it passes through the generic points, then the jet space of Y restricted to V is C algebraic. Right, so you're restricting to some V that sort of nearly lies in the constants, and then saying that the jet space also nearly lies in the constants. Remember, C algebraic was the same as C internal.
So here you're not taking it at a point when you say jet delta?
Yeah, so this is the jet bundle
A bundle of the whole.
thing, but I'm restricting it to the fiber above V.
Yeah.
And you're fixing the,
Yeah,
Fixing the,
right, because so the idea, like restricting it is like looking at the generic type over something. Right, it's like looking at the generic type of the jet space over the defining family for V, for the point V.
yeah.
So do you have some sort of intuitive explanation of why sort of the standard issue internal over internal two-step analysis cannot occur in a jet bundle? Like, why
Let me see
couldn't
if I
it
can-
be that the jet space over a point A is the set of solutions of x prime equals A.
Yeah. So the idea is sort of that, right. So if you have, so you have A, which is over B, which is over D. So that means that B, so A over B is internal,
Yeah.
right? It is that, so B is sort of algebraic over D. So what you can really do is sort of move, like, basically the way the proof works is basically you, right, having some internality is saying that there's some kind of algebraic relation between these two things.
Yeah.
And when you have algebraic relations, you have a finite to one map
Yeah.
in some way. And when you have a finite to one map, you get an isomorphism of jet spaces. Right, so this is like if you have finite to one maps and varieties, you get isomorphisms for the tangent spaces.
Yeah.
Except where, well, generically, yeah.
Yeah. So any kind of algebraic thing gives you isomorphisms of the jet spaces, and any kind of injection gives you a surjection of jet spaces. And then basically what you end up doing is you come up with all these jet spaces sort of involving D and also independent things. And then you can map them by either surjective maps or isomorphisms all the way until you get the jet space of A. Right, so it's sort of this property that that algebraic relations of the points that you're taking the jet spaces over give rise to isomorphisms of the jet spaces. So, yeah. And I can talk more about the proof in the afternoon. And then I guess one remark that, let me see, did I write it? So I wrote it over here, right? There's the second point that you had to pass through the generic points. Okay, when you took this V subset of Y, it has to pass through generic points. So this example, so there's a variety in two space, defined over the rationals. So if you look at the tangent bundle, and I call that Tx to x, and you look at the fiber over the constant points of x, then this is not C-algebraic. Right, so the constant points of x, that's sort of trivially C-algebraic because it lives in the constants. But if you take the fiber over it, you get something that's not C-algebraic.
I'm terribly sorry. Can you remind me what C-algebraic is?
So this was like internal. Right, so
Yeah.
let me see. So there's no, basically there's no way of taking like a finite to one projection two ways onto some constant variety. Right, or the type, the generic type of the tangent space over one of these points. That's not C internal. Right, so
Wait one moment. So
Yeah.
why does this not contradict your theorem?
so this one doesn't pass through the generic points of this guy.
Right.
Oh, differentially generic.
Yeah.
Yeah. Okay, we have to remember that. That's right. Pass through the generic one.
Okay.
Yeah, sorry.
Okay. Now I
Yeah.
believe it a lot more.
Right,
Oh,
it's about
okay,
independence,
okay,
right?
Yeah,
okay,
constant.
okay.
Yeah, and non-constant.
Okay.
Yes.
Okay.
Yes.
Okay.
They're not vector space-like. That's nice. What is it?
Sorry? Oh, what is it? So it's given by and then the idea is that the constant points have to set x equals y,
Yeah.
right? Which ends up meaning that you end up not passing through the generic.
Oh, not even the algebraic generic.
Differentially generic.
Yeah.
That's a big condition.
No, but I mean, it's not even algebraically generic now.
Yeah.
Culture generic.
Because algebraically, you're just looking at
Yeah,
anything, right? You're only listing these things.
right, yes.
And then the thing is that if you restrict to the tangent space, then you end up getting, so you end up seeing like a logarithmic derivative show up,
Yeah.
and then it comes from a non-splitting of an added
And I'm thinking of a differential algebraic group that maybe is an example too. Contains the constants, but that's the one I was just mentioning before. No way is its underlying variety differentially birationally isomorphic to any constant variety. Or anything, yeah. But I had to fight over that. Oh, I mentioned it, because everybody said, but that's just algebraic. That, no, it's not algebraic. Yes, it is. For years.
So somehow, for vector spaces, if you start with something over the whole field, then you look at its constant points, and then tensor it back with the big field, you get the original thing back.
So vector space, you take constant points, tensor back, yeah, because of the...
Yeah.
Because of this basis business, because of differential closure.
Yeah.
Whereas for this variety, or for this difference variety,
Right.
you take the constant points, you try to base change it back, but you're stuck on the diagonal. So you get
Yeah.
something much,
Yeah.
much smaller.
Yeah.
Yeah.
Okay. I guess you could also cook up let's see. What happens if you take X, a variety, a differential variety on one-dimensional space that just says delta X equals X? Then the constant points will be just the origin. And then it'll be even less generic somehow.
Yeah, and sometimes the constant ones aren't big enough.
Yeah,
Yeah.
right?
Yeah, so you have to figure out the tangent space. Because there is something happening where the tangent space sort of changes on the diagonal.
I see, okay.
See,
Okay.
we don't tangent space, we go to infinity.
Well,
In differential algebra, we don't use the prolongations. So everything takes place in K. Big K. So I have to think in terms of, you go, when you have derivatives, you prolong. Yeah.
So maybe we should continue this
Alright.
at 2 o'clock?
Yeah, thank you.